In statistics, we're always interested in variability. If I take a sample from a certain population and use that sample statistic to try to estimate something about the population, I would like to know how reliable my estimation might be. So here, I could see that the majority of the time, taking a sample from this population, I could get anywhere from about 25% to about 75% red in my sample, when the true population proportion is actually 50. So that's quite a lot of variability. Is there a way to reduce the variability? So let's look at a couple possibilities. One would be to increase the population size. What if I had a bigger population? Would the samples be more accurate? So let's make 500 red and 500 white instead, using samples of size 20, and I'm going to go ahead and compute 5,000 runs of this. There is no difference at all in the distribution of the sample. It still goes from about 0.15 to about 0.85. It looks exactly the same as the one I did before. When I had a sample of size 100, it still centered at the same place. So changing the population size doesn't have any effect. So it has to be something with the sample size. So let's say instead that I take a sample of 50 instead of a sample of 20. Let's make the sample size bigger. Let's do 5,000 runs again. Now notice with a sample of 50, there's a lot more different statistics I could get. I could get here 0.52, 0.54, 0.56, etc. So this is broken down into smaller bars. But let's look at the spread. Notice that before, almost the entire distribution went from 0.15 to 0.85. So this goes from 0.28 to 0.74. So already we see some reduction in the variability. Let's make the sample 100 instead of 50. Let's do 5,000 runs. Okay, once again, this goes from 0.34 to 0.68. Once again, it's a reduction, and you can see the majority seem to be between about 0.35 and about 0.65, which is quite a bit smaller than what we had before, where we went from about 0.2 to 0.8. Now it's more like 0.4 to 0.6. So we're seeing the majority of the time we're going to be within 10% of the true population proportion, where as with a sample of 20, it was more likely to be within 20% of the true population proportion. So we can see that sample size does a great deal in reducing variability. So to summarize, if we go back here, changing the population does not change the variability of the sample proportions. But as the sample size increases, the variability, and I'm going to maybe say the variability of p hat. Okay, so we're talking about of p hat. The variability of p hat does decrease. And I have this summarized if you wanted to look at the printed notes that are online. I have this summarized using a series of graphs showing the decrease. Something else that's interesting to look at on this is if I wanted to look at what I did on my graphs is I said, let's say what proportion of the distribution is greater than 0.6. We see that only 2% of the time are we going to get something bigger than 0.6. If I go back to 50 as my sample and do 5,000 runs and make this 0.6, notice in this case about 10% of the time we're going to get a sample that's bigger than 0.6. If I go back and change this to back to 20, let's see how often we're going to get something bigger than 0.6. So about 25% of the time, my sample proportion will be bigger than 0.6. So this gives another measurement of how the degree of accuracy we can expect with different sizes of samples. In future videos, then we're going to formalize that rule. Exactly how does the sample size affect the variability in this sampling distribution of sample proportions.